Good morning. Today is July 15th, and this is the CNPS Saturday Morning Science Chat. And we've been looking at things involved with atoms and atomic models. We first looked at some evidence of alchemy or like low temperature fusion, like cold fusion, and the possibility of that happening. But that completely contradicts the existing model. And the existing model is that we've all been shown in mainstream is this tiny little nucleus in the middle with these far-flung electrons. I mean, these electrons are so far-flung that if the nucleus was like the size of a tennis ball, the electron would be orbiting outside the city limits pretty much, I mean, really far away. And so that's the existing atomic model. Last week, and the week after that, we explored some atomic data. And there's all kinds of atomic data. We see a lot of periodicity in the data. So any atomic model needs to explain that sort of behavior. There's some mysterious things like when uranium fissions, it fissions in uneven lumps, basically at basically 1/4 and 3/4 type pieces, which is hard to explain by any of the existing models, the most common ones being the shell model and the liquid drop model. But also, I was discussing that book, both of those models are mutually incompatible with each other. So while each of the models can explain some of the data, there's no one model that can explain all of it. And then just last week, we were exploring Tufsky's Earthodynamics, which was translated by Slobodan. So, in that theory, there are things called amers, which I think form the basic substance of space, and that things like protons and stuff were built out of these amers and kind of toroidal ring kind of structures, and then the atoms were built out of that. Now, this week, we have with us Bill Lucas, and his website is Common Sense Science. And I believe, Bill, he has another atomic model to present. So I'm going to let Bill go ahead and explain how he thinks atoms are constructed. So go ahead, Bill.
Well, thank you, Franklin. What I found as we talk about our different approaches to the atom is there's some compatibility, some similar ideas involved in many of the different models. And these compatibilities explain certain types of phenomena. And so the the important thing, I think, when we do our presentations is to understand what is in common between the different models and what that enables you to explain, and what is different and what the differences contribute to explaining things like the atom and the nucleus. And I'm sorry I was not there last week. I was very interested in that topic, but I had grandchildren that I was picking up in Ohio, and I was traveling all during the day in a car, and I couldn't be on the phone and driving the car at the same time. But getting back to the work that I have done on the atom, and David Bergman and other people in Common Sense Science, where no one person does everything, we contribute to one another's work. It is based on the concept that the electron is made of toroidal rings. At first, we thought it was one ring, and then we discovered that the scattering data on the nucleus of atoms would enable us to see that the nucleus or even an elementary particle like a proton, consists of three subparticles. And those subparticles have what we call fractional charge. They're one third the charge of the electron and two-thirds the charge of the electron. So that meant that it's very likely the electron is not a single, made of a single thing like a toroidal ring, but made of three of them. And so when that concept was fully explored, we found that we were able to explain the interior structure in terms of toroidal rings of all the elementary particles that we have, which is 96 well developed, well defined elementary particles, plus there's 300 or 400 more that are just a function of a theory, but we don't have good experimental evidence for them. So, but we do have good evidence for 96 of them, of the elementary particles, and so some explanation needs to be made. You can't uh, entirely ignore that when you're trying to do a theory of the atom, because you've got electrons and protons and possibly neutrons in the nucleus, and so you got three elementary particles there, and you've got to have some kind of compatibility with the theory of elementary particles. Why are atoms just made of those particles? Why not all 96? You know, and so you got to be able to explain some of those things. Um, the work that we have done on the toroidal ring, we thought we were we were originating that, but as we did more research, we discovered that a person at the Smithsonian had done a lot of work on toroidal ring electrons uh, in the 1918 and 16, those times. And then people at MIT did work on it, people at Harvard, people over at Oxford, and they're all ahead of us before we were even born. So our work is not as original as we thought. And then we discovered that um, people had worked on theories of matter long before that. In fact, um, the Greeks, ancient Greeks who lived in 300, 400 BC, they claim that Moses, the Hebrew lawgiver, was the first proto scientist and the inventor of the theory of matter being composed of monads. And they said, and the Indian Jains in India said the same thing. And they were even 400 or 500 years earlier than the Greeks, and but not as well known to us. And so, but the Greek historians said that they didn't. The Greeks did not give any credit to Moses, and they also changed his theory of matter to suit themselves and their religion. And so, but there were certain features that remained. And if you look at the features in the Greek and you compare it with the features in the Indian Jain, you can see that what they had in common was probably what Moses said, and what they have that's different is maybe deviations from what Noah said. But we don't, or Moses, but we don't have any written documents directly from Moses. So it's all kind of up in the air. And this information went along the trading routes, what we call the Silk Road, and it went from Greece all the way to India and to China and even to Japan. And we see evidence of that historically and in documents that they produced, but of course much later. Um, so the idea of the monad that the Greeks wrote about, and also the Indian Jains, was that the properties of matter were determined by the geometrical structure of monads being combined together into a larger structure. And So that was an interesting idea. And to give you an idea of how important that was, when the Greeks established their academies, which is like our universities, um, they had a sign over the door. It said, "Let no one ignorant of geometry enter here." And why did they have that? These academies were academies of natural philosophy, and they were trying to explain the physical universe and everything that you could observe about mankind and nature and animals and the sun and the moon and the stars, all that kind of stuff. And they felt that geometry was so important that it was the most important thing you could learn. And so uh, they talked about the monads combining to form dyads and triads and uh, different geometrical structures, and they tried to explain the nature of elementary particles, what we would call elementary particles today, in terms of these structures. And so, as we have worked at Common Sense Science on this problem of explaining the different elementary particles, we have discovered that there are certain symmetries and geometrical uh, forms that these monads which are also known as toroids, come together to form things. And you can experiment with this with magnets. You can take ring magnets, which is sort of equivalent to an electron in a way, or a monad, and you can um, put them together in different combinations, and you can try to pull one of the magnets out of the structure and measure the force it takes to remove it. And so if you do that and you start putting magnets together in different geometrical structures, you see that some geometrical structures are more tightly bound than others. And in fact, if you know the structure of the atom, we have what we call electron shells. We have a shell of 2, a shell of 8, a shell of 18, a shell of 32, and a shell of 50. And believe it or not, just the use of ring magnets can confirm that those are the most well bound, tightly bound structures geometrically that you can have. And the but there's a little bit more to it than you might imagine from just doing the magnet experiments, because um, in the work that we've done in electrodynamics, which of course is governing the outer electron part of the atom, we have found that if you use all the empirical laws of electrodynamics, you get a more enhanced electromagnetic force than people like Maxwell got, who only used 4 of the 6 empirical laws. And when you do that and you combine that with conservation of energy, so you use an energy potential instead of a vector potential, which is what Oliver Heaviside did with Maxwell's work, uh, you find that you get radial terms with spherical symmetry, you get velocity terms, that's what Maxwell got, but you also get acceleration terms and first derivative of acceleration with respect to time, which we call radiation reaction terms or recoil terms. So the work that we did at Common Sense Science, we have these 4 types of terms, and if you do it with vectors, there's 2 types of vectors. There's a vector that's just r for the radius, or v for the velocity, or a for acceleration, or dadt for the radiation reaction term, which is kind of has spherical symmetry. But there's a second term for the velocity and the acceleration in dadt that involves a cross product of r cross v, or r cross a, or r cross dadt. And that uh, type of structure in mathematics and in vector uh, geometry and that sort of thing, is known as chiral symmetry. And so um, the electromagnetic force appears to be a combination of spherical symmetry and chiral symmetry. Well, if that's valid, that means that in the case of an atom where electrons are being bound together in certain structures, and they're toroidal ring type structures, um, there's going to be a particular symmetry. And that symmetry is going to uh, determine the size of each of the shells that you have for electrons about the nucleus. And so, um, so that symmetry becomes very important. And so we're able with just using mathematics and solving the six simultaneous equations or six empirical laws of electrodynamics simultaneously to get the most general form of the electromagnetic force and the electromagnetic field. And we're able to um, now predict the size of all the shells from electrodynamics alone. No quantum theory, just electrodynamics. And in the properties of a magnet or a toroidal ring. A toroidal ring has a magnetic field associated with it. And by the way, in the empirical laws of electrodynamics, when things get closer together, like toroidal rings or whatever, it turns out that the magnetic force is stronger than the Coulomb electrostatic force. So the motion, the terms related to force for motion, predominate at very close distances, but not at far distances. And so it's very interesting to see that. So we've been able to uh, determine experimentally with magnets the uh, the different geometrical combinations that produce shells, uh, and we're able to determine the relative strength of the binding of each size of shell. So, for instance, a shell of 2, which would be for like helium, is not as strongly bound as a shell of 8. And a shell of 8 is not as strongly bound as a shell of 18. But a shell of 32 is not as strongly bound as a shell of 18 either. And neither is a shell of 50. So what we see is there are certain peaks of highest uh, what you would call binding. And when an atom, for instance, decays, if you have a nucleus that decays, you have the same kind of shells in the nucleus. When it decays, it's going to want to give priority to the more tightly bound shells. And so that determines what type of structures you're going to have when a nucleus decays. In other words, if you have uranium decay, uh, it may just give off an alpha particle, but it may come apart and produce two large size nuclei, or three even. And what you find is that those tend to be the more tightly bound ones. And so the liquid drop model of the nucleus kind of simulates that in some ways. But this geometrical model using the properties of magnets gets it more precisely than even the liquid drop model. And it also enables you to determine how the particles in the nucleus will come together to produce what we call the nuclear spin. The nuclear spin is a type of magnetic field of the nucleus, and you can measure it experimentally. And we have measured it for 3,500 nuclear isotopes. So we've got a lot of data. And unfortunately, the politically correct theory of the nucleus, which is a quantum theory um, with a nuclear potential, um, shell model theory, uh, it fails to predict 1,300 nuclear spins. Now, that's pretty bad for a theory to not be able to do that. The approach that we have taken, which is empirically based in the sense that we're using properties of magnets and that sort of thing, we are able to predict without any adjustable parameters or anything of that sort all 3,500 nuclear spins. So that appears to be progress to us. Uh, is we're the only? Do we have the only theory that does that? Only, well, there's none politically correct that have that, but there could be others that do it. And for instance, this one that spoke last week, because he's using the properties of the toroidal ring and that we're using, if he uses it properly, he could come up with the same conclusion. Uh, and so, uh, so uh, we'll find that different people's model of the atom can explain things that they, particularly when they have things in common with another model. And they where they're different from another model, that could be a different story. They may give a different result than the other theory. And so anyway, that's how we have worked. And Uh, it is interesting. When I had one son that went to a science and tech high school, and he had to have a 4-year science project, which he didn't like, but he had to do it. So he asked me if I had something interesting to do, and I suggested a new theory of the atom. And he used some of this material, and he performed some of these experiments with magnets and that sort of thing, so that it could be understood by the students in his high school and that sort of thing. And he actually made it to the International Science Fair. He had to win the local science fair in his science and tech high school, the regional science fair for a certain section of the state of Maryland, and then the grand prize winner at the regional science fair got to go to the international science fair. So he was the 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 winner of that science fair for all the projects in all the fields, and with a theory of the atom. And he went to the international science fair, and there it was very controversial, a new theory of the atom. But the judges for the grand prize chose his project over all of the other projects from all the other countries that participate in the international science fair. And so doing that is almost equivalent to winning a Nobel Prize. It's a little short in terms of cash. He only got about $300,000 worth of cash, not 1.5 million, or that if you're the sole winner of a Nobel Prize, that's what you would get. I think they're having financial problems now. It's 1.3 million, but it used to be 1.5 million. And but that money he used to go to Caltech, the number one school in physics in the United States, and Harvard, the number two school. And he got to explain his theory and talk to all the theoretical people there, many of whom were Nobel Prize winners. And so, so anyway, a lot of people were interested in the work. A lot of people were antagonistic to the work because it invalidated their Nobel Prize if it was true. And so you got all this kind of stuff going on in the scientific community, and also a lot of people have big grants related to certain ways of looking at things in physics. So, like for instance at CERN, you know the had they researched for the Higgs boson. I mean, they spent $1 trillion on that. And someone coming along and said, "There's no Higgs boson. It's clear. Here's the theory of elementary particles. You don't need a Higgs boson." Well, they wouldn't like that. In fact, of the 17 principal investigators there, 15 said they didn't find the Higgs boson, but 2 said they did, and they needed, because they had spent so much money, to justify what they have done. So They went with the two, not with 15. They didn't go with the majority. They went with the ones that would keep them in good standing with governments and who had contributed all the money. So anyway, those are kind of things that go on in the field. Now, uh, what really helped my son's work, and I worked with him on this too, in the theory of the atom was NASA measured the emission spectra of hydrogen and helium atoms in space. When you do it on a laboratory on the Earth, there's certain energy ranges you cannot measure because of the containers that you have to hold the gases in, like hydrogen and helium. And the certain types of energies uh, won't go through the glass container or whatever, and so you can't see it. But in space, you don't have to have a glass container. Space has helium and hydrogen spread throughout the universe, so you can just put your uh, what do you call it, grating out there in space and split the light that's coming in into different frequencies and wavelengths and then record it either on photographic paper or some other type of recorder. And so NASA had done that, and they had found a large number, about 100 or more, uh, emission spectral lines in the extreme ultraviolet, where you cannot measure it on Earth, for both hydrogen and helium atoms. Well, it turned out that neither the Bohr model of the atom, nor the Schrodinger model, which is a quantum model, nor the relativistic quantum model, which is the Dirac model of the atom, predicts any spectral lines at all from hydrogen or helium in the extreme ultraviolet. And the reason for that is that they have something like a point electron orbiting the nucleus. And these energy states of the electron that would give rise to that cannot be formed from a point particle. They require a continuous loop of charge, which has different properties than a point particle going in an orbit around the nucleus. And so the question there was, well, does that data that NASA took, is that sufficient to falsify the point quantum electron models of the atom? Uh, and we took the point of view that it was. In other words, if you have a theory of the atom and it cannot predict the states in the extreme ultraviolet, and we discovered that there were just as many states in the extreme ultraviolet as the regular uh, frequency range that people use for the atom, for their theory of the atom. And but it's higher energy. And the judges at the International Science Fair were really impressed. They happened, by the way, to be from NASA, which was lucky for my son, because if they'd been from some other institution, I suspect they would have not paid as much attention to the fact that he was explaining NASA data. and but anyway, uh, in the work that my son did, he was able to explain all of the empirically measured emission spectral lines in the extreme ultraviolet within the experimental accuracy of the measurement, which was very precise, more precise than any measurements made on Earth, because in space they were able to see not only the original spectral line, but they were able to see the different orders of those lines. So if you ever watch a rainbow, you've seen sometimes you'll see two rainbows. The first one, the primary one, is bright and easy to see. The secondary one is fainter And one time I saw three, the third order, but it was very faint. And so that's the way it goes. And they were able to measure at least 7 orders of every spectral line, just about that NASA measured. Uh, and in the energy range they had. So that data was the most accurate um, atomic data ever measured. And the theory of the atom that my son submitted with his science fair project explained every line that they observed, every emission spectral line, and all the orders that they saw. And so uh, that was considered quite a feat. And that's why my son was granted the grand prize at the International Science Fair. And so uh, the challenge now to the uh, politically correct models of the atom was that they can't explain a single line in the extreme ultraviolet for hydrogen or helium. And they involve in their theories assumptions that are known to be false. And so here's some of the data right on the screen. You can see. Thanks. And the one of the assumptions is that the electron can orbit around the nucleus in a stable state without continuously emitting radiation. But in every accelerator experiment that I've ever worked on and that I've ever heard of, whenever you have a charged particle like an electron or a proton or a muon or a kaon with negative charge, when it's going in a circle, it radiates energy continuously. And the laws of electrodynamics say that whenever you accelerate a charged particle, it has to radiate energy continuously. So the people who are doing the theory of the atom are ignoring the experimental results and ignoring the laws of electrodynamics when they make a theory of the atom where the electron orbits the nucleus. And the other thing is when an electron makes a transition in those theories to emit light, they have it occurring instantaneously, but there's a distance involved between one orbit and another, and they ignore that. And so there are a number of problems. And what has happened is, in order to retain these theories, the scientific method was changed to remove the role of logic. Now, why would they want to do that? In the axiomatic or logical scientific method, if any assumption of your theory is known to be false, your theory cannot be true and it's falsified. But they didn't want that, so they took that out. And if you think about what were you taught when you went to school about the scientific method, this change was made, I guess, around 1910, 1920, in that time frame. If you want to, if you look at that, you see, from what you were taught that you form a hypothesis in science, you make a prediction, you perform an experiment to see if your prediction is satisfied, and if it is, you justify that as a proper scientific theory. But the logical axiomatic approach, or scientific method approach, says no, that's not sufficient. If any assumption that you require for your hypothesis is known to be false, your hypothesis is falsified no matter how much data it can predict. So there's the difference. And so the problem with the politically correct theories of the atom is they're falsified on the basis of their assumptions for their hypothesis, and they're falsified because they can't predict all the data. So But have they been falsified by the politically correct scientific community? No, because they removed that from the scientific method, and so they don't count it. They don't want that. They want to keep the theories that they have, and so it's a problem. And it's not just the theory of the atom. The theory of quantum mechanics has this problem. The theory of special and general relativity has this problem. The Even the theory of electrodynamics, because they didn't use all the empirical laws of electrodynamics, has this problem. And if you go into the standard model of elementary particles, they have the same problem. It's throughout all of science. They have changed the scientific method so that it's no longer a valid method. It leads to truth. And
So Bill, can we get more into your atomic model?
okay, well, my atomic model, uh, it uh, it it satisfies the laws of electrodynamics. It's stable for the stable
And why did you interrupt him? I thought what he was saying was really good. Why are we changing the subject just because you want to, Franklin?
Because we're really exploring the nature of atomic models. So
Yeah,
while what he's saying
but
is
I
very
was interested in knowing why, okay, the mainstream is not paying attention to Bill's model.
Well, it wasn't just me. I mean, Parsons at the Smithsonian in 1916 gave some of these same arguments, and people at MIT gave the same arguments, and people at Oxford gave the same arguments. And I wasn't original with me, but I didn't know about it at the
I'm
time.
perfectly aware of that, Bill. What I'm more, you know, all this. My question is, you make a good case. What is their objection if they have an objection to these models?
Okay, it's kind of complicated, but I'll try and explain it for you. In the late 1900s, the scientific community decided to go for a naturalistic philosophy of science. Okay, and what that meant was they were rebelling against things like the Protestant Reformation, and there was a spiritual revival in the 1800s, and they didn't want to have anything to do with religion. They wanted to get religion out of science. So with naturalism, they said the natural laws of science should be able to explain everything we observe in science. And so they started talking about evolution. They started talking about quantum mechanics, uh, and these type of things, which are very different from classical science. And so when they got challenged on this, they realized they couldn't win if they kept logic in the
Can I
scientific.
interrupt you a bit here,
Sure.
Bill? It sounds to me like what you're saying is that classical science was based on experiment and they wanted to change that to something else.
It was based on experiment and logic. They wanted to get rid of the logic part because they couldn't maintain the theories that they liked from the naturalistic point of view. In other words, let's just take a simple case. What's the origin of the universe? Well, according to quantum mechanics, it was something like the Big Bang. From a religious perspective, it's God. And we know the mechanism by which he created because it's recorded in the Bible. And so if I do science and I discover, oh, the electromagnetic force is a universal force. We don't really need a strong interaction force or a weak interaction force. And the force of gravity is really electromagnetic, and the force of inertia is electromagnetic. And, well, what am I doing? I'm supporting religion. Well, I want to get religion out of here. you know, I don't want to have any religion. I want science to be independent of that. And so that is what was going on. And most of us, including myself, when I went through school, I didn't know a thing about that. And but now that I've had 40 years of being out of school and studying, reading around and that sort of thing, I've discovered this stuff. And the internet has helped because it made many of these documents available, which I never knew about before. And we're learning more about that. So a person who doesn't want to be religious will say, well, I like the idea of naturalism. And if that group of people becomes a majority in the scientific community, then they'll make that the rule. And so we have what's called the postmodern philosophy of science with silos. And we have a silo for each field of science. And they determine what will be allowed and what will be not allowed, what will be politically correct and not politically correct. And um, that was put in place in the late 1960s. And I, unfortunately, was one of the first people to find out about it. I lost my job by giving a talk showing that the theory of relativity, special relativity, involves a number of assumptions that we know are false by experiment and observation. And that was not allowed. And so the the head of the Department of Energy and the National Science Foundation, those two organizations, wrote a letter to the university where I was working and said, this fella said this, and that's not allowed. We want him fired in 24 hours. And I was.
So the bottom line is that, and as I gather what you're saying, is you're saying that according to the modern scientific method, experiments don't matter if they refute our theory, but they do matter if they support our theory.
Yeah, but they're more specific. Um, if I have a theory of gravity and an inertia, like Einstein's general theory of relativity or Newton's laws, and I'm looking at, say, a spiral galaxy, and I find I can't predict the structure, the shape, and the velocity of the spiral galaxy. I miss it. And so, do I falsify my theory? No, I invent dark matter and dark energy to fill in the gap. And is it a tiny effect? No, 96% of the effect is from dark matter and dark energy, and 4% is from regular matter and energy. And so we do that kind of thing in science. And if you were to look at the current theory of elementary particles called the Standard Model, which is a string theory type model, it has been, depending upon which version you look at, between 19 and 29 adjustable constants, which represent currently unknown physics. And that's accepted. And if someone like me comes along and say, well, just from electrodynamics, I can predict all these properties of the elementary particles which you can't predict, well, they don't like it. I'm using logic. I'm using geometry. I'm not using quantum mechanics. I'm not using strong interaction, weak interaction. I'm just using electrodynamics. They can't stand it. And so if I go to speak at a scientific meeting, international scientific meeting in this country, they'll pretend I never came. They won't put my paper into proceedings. But if I go to a country like Ukraine or Russia or Spain, they accept me because they don't have this rigidity. They're a little more practical. They're trying to make progress in science, and so they do that. But in our country, particularly, where so much money is spent on research, and there's such a competition between universities to get money and to get prestige, that they don't want to allow any competition with these other theories, which might put them out, if you might say, disprove what they're doing. So that's what we see. And that's why many of us have their various insights, and we see something wrong with the politically correct theory. If you're in a university or a place like that, you may find yourself fired if you try to tell too many people about it. But and we have members who were in the Natural Philosophy Alliance. I remember one time we took a survey, and I think there were nearly 500 members who had lost their university positions on these kinds of issues in the United States. So it's not something that's just an isolated person here and there. It's something that's been going on and continuing to go on.
So the bottom line is that any alternative model for the structure of the atom that anybody comes up with out of this forum is really basically wasting their time.
Well, not if you're interested in truth, but if you're interested in making a living in the university world or the scientific world, yeah. Because see,
Well,
I had to leave the scientific world and go into the computer field just to make a living because uh, once you were blackballed by the uh, Department of Energy and the National Science Foundation, you can't go anywhere, get a grant. No university wants to hire you, even religious universities don't want to, and so that's because they can't get any federal money if they do that, and everybody wants money.
So Hans, do you have a question? Hans had his flag up.
Yeah, I have a question. I looked through the site and I saw a lot of nice drawings, all relating to each other. But then I nowhere see a theory that is explaining what these drawings are meaning. So where do I find the theory?
Okay, if you go, there's a place where on the, let's see, there's a way to see all. We publish a journal called Foundations of Science that's in a newsletter that goes out from Common Sense Science, and from this website you should be able to see papers. I think go down to papers.
Yeah.
Okay, and now here are the papers, and you can
Ah, yeah.
see the experiments. For instance, the ones on the atom, we show the experiments we were done with magnets, which show what the stable structures are that are possible for electrons in an atom. And so you see the experiments we perform. These are not theories. These are experiments that show what the geometrical combinations of toroidal rings are that could be used to determine a common structure. And so that's what we use. And then we actually derive the formula for the uh, energy that can be emitted from an atom, and using that structure and the laws of electrodynamics. And much of that work is very similar to what I call antenna theory. In other words, if I have an antenna and I want to give off a certain type of radiation, I have to have a certain type of wave in the antenna, electromagnetic wave. And if I want to give off this same radiation continuously, I have to have a certain type of standing wave. And so it is the formulas for those standing waves, which we have gotten experimentally from antenna and other things that enable us to see that. Also, we cover the photoelectric effect. The photoelectric effect was used to justify the idea that a photon was a particle. And what we show there is that when the photoelectric effect that Mrs. Einstein did at Weber's laboratory was repeated about 10 years later with amorphous metals, not crystalline metals, but amorphous metals, there's no photoelectric effect. And so it shows that the concept of the photon being a particle is not valid experimentally. And what if you look at the optical chips that are made for computers, you'll find that they have to put little crystalline antennas in the chip to make the optical chip work. If you don't put it in, you don't get any effect. And so being a computer person, I've noticed that, and optical chips seem to be part of the wave of the future for higher speed performance and everything like that. And so we have all this evidence now that has come in. And for the theory, all we use is the 6 empirical laws of electrodynamics solved simultaneously. And that enables us to explain all the mechanisms for radiation and absorption, for emission and absorption of radiation from the electrons in the atom that are made of toroidal rings. So we don't have
Bill,
any, we have added no theory. All we have added is done is solve things simultaneously from the empirical.
Bill, it seems to me that the main, there's a lot of complexity in what you're talking about. Seems to me the main issue has to do with the toroidal structure, if I'm not mistaken. And just sort of a side question here. Do you remember Robert Keene? Do you know who I'm talking about?
I'm not sure. Go ahead.
He died, I think, a couple of years ago. I know he participated in a couple of our conferences, and he was very keen on this toroidal soliton theory. There seem to be a lot of people working on this. And I guess my question goes to, given the fact that there's a lot of people talking about this, why is it that mainstream physics continues to ignore this whole idea of the toroidal structure as a fundamental structure?
It's very political. In other words, if we train the high school students and stuff like that in this material, so they eventually became the majority in the scientific community, I think that we would see that. Now here you can see some of the experiments that were performed. It's just on the screen right now with toroidal ring magnets, and you can see the north and south poles of the magnets and how they line up. And that is what we observe experimentally when we do experiments, is that this structure is there. And if you put an odd number of magnets, they won't form a ring like this. They have to be an even number. And in order to have the chiral symmetry, you have to have left and right hand symmetry in the atom that uses these structures. So that's why you go from a shell of 2, the next shell is not 4, it's 2 sets of 4 in order to have the left and right hand symmetry. And so there's a lot of things going on. Here's the measurement of the binding energy of the ring magnets in different structures. And you can see, actually, I think I misquoted this, but you can see the shell of 2 is not as strong as the shell of 8. The shell of 8 is the strongest. Then the 18 is weaker, and then 32, and then 50. And so you can see that, and we measured that, and we had to build apparatus so we could properly measure it. And the only other person I know who did that was Parsons at the Smithsonian in 1916, 18 timeframe. But he didn't do it the way we did. He did it with current loops instead of ring magnets, but the same idea.
I think, Harry is right in that, at central to this theory is this Bernoulli's ring model of elementary particles, right? So, but this would be
yes.
Toroid, please. Toroid.
Yeah. The toroid, in other words, if our theory of the atom is incompatible with the theory of elementary particles, we got a problem, because we are claiming something for electrons and protons and neutrons that is not in agreement with with the area of science that deals with elementary particles. So you have to be able to explain both fields simultaneously. In fact, you have to be.
Here's the issue, in my opinion. Okay, I'm just going to give it to you fairly straightforward. You can comment on it if you want. I don't see that a spinning point particle can generate a magnetic field. Sorry.
I don't either. And the electron's not a point particle. When I was at William and Mary in graduate school for my PhD.
Well, isn't that really the weak point in everything that mainstream is saying? Because they're assuming these things are point particle structures at some point, or am I wrong in this?
Yes, but what they
I guess
fudge
I'm
it.
wrong, or what?
Well, they fudge it. What they do is they have the uncertainty principle, and with the uncertainty principle, they have these point particles emitting and absorbing other particles that gives them the effect of a finite size, but it's not a toroidal ring.
Well, that's not really a structure at all, as far as I could tell.
Well, but they claim it is. And in quantum mechanics, the universe is not physical in the classical sense. It's more probability type things.
So let's just sort of, I guess the problem I have with the, to be quite honest, as soon as they say spin, I'm trying to imagine, to me, I can't, I don't see how a proton or a neutron or an electron, which is to me, it's a point particle model. And I don't see how a point that's spinning, even if you give it a finite size, is still going to create a magnetic field.
Well, wait a minute. There's a couple of points here. Do you know the difference between a magnetic moment and the spin of a particle?
Well, I'm assuming that they infer the concept of spin from the magnetic moment that's measured.
Well, we measure the spin also, but it's not.
You can't measure
It's not
the
a
spin.
rotation that we're
How is the spin measured without measuring magnetic field?
The spin is a magnetic property, but
Okay.
you've got to look at the toroid. Here's a picture of a toroid on the screen.
Well,
Okay.
let's just back up, Bill. The bottom line is that the whole concept of spin is really based on the measurement of some kind of magnetic property, as you say.
Right, but the spin has nothing to do with rotation.
Well, I'm assuming that it is because that's what they call it.
I'm just trying to say that in the politically correct view, spin is a magnetic property. It is not a rotation property. If we can go back to.
Well, okay, but now here's my point. This is what I've never really understood. How does a point have a magnetic field?
Well, they ignore that. They say, well, it's produced by the the uncertainty principle and that sort of thing. And so you can't talk about the point particle as much as what is being produced and what is being absorbed by the point particle.
There's no real point particle. It's just a. To me, it all sounds kind of vague.
Well, you see, you're trying to
say. What I gather you're saying is that it's a quantum mechanic property of whatever this object is, but we're going to assume that it's a point particle for the sake of simplification. Is that kind of a description of it?
Well, I think what you really need to understand is that in quantum mechanics, there's no physical particles. There's no physical things. It's all quantum mechanical. And that's what has been the big problem in the scientific community is that nobody understands quantum mechanics because they have this classical notion of particles and waves and that sort of thing. But that's not what quantum mechanics has. The wave function in quantum mechanics is not a physical thing. And when you realize that, you say, well, how do you compare this theory of quantum mechanics, which is non-physical, with the physical world I'm used to seeing? And the answer is, well, you just don't understand quantum mechanics. And it's another way of looking at it that's at a higher level than what we did in the past. And
well, that's kind of their standard answer to
right.
objections of their concepts.
The ring model, the toroidal model, what it does is the magnetic moment of the particle, say the electron, is determined by the current, the charge that goes around the circumference of the ring. The spin is the magnetic moment produced by the current as it goes around the cross section of the ring. So in this ring model, you have two motions. You have the motion around the circumference, and then you've got the motion around the cross section. And so the cross section they call the spin, and the large circumference they call the magnetic moment. But they're both magnetic. But
So
one
Bill,
is, yeah,
so the difference between the two is that basically the spin is around the minor axis of the toroid, and the magnetic moment is the major axis of the toroid. Does that sound correct?
that's right. That's right. So, and if you look in toroidal parameters and that sort of thing, you'll see those axes you're talking about, and how they're prominent and play a role. And it turns out that Planck's constant can be predicted by the physical properties of the toroidal ring, whereas quantum mechanics cannot predict the value from electrodynamics, the value of Planck's constants. In fact, if the work that common sense science is doing is correct, that the electromagnetic force is the universal force and there is no other, then all the standard parameters or constants of physics should be predicted from electrodynamics alone without having to make any measurements experimentally. We should be able from the theory to predict all of them. And that's one of the goals we have. So we haven't succeeded in doing all the areas yet. We're still working because we have a limited capabilities, but we're making progress, and we hope to be able to do that. And so one of the things I point out when we meet with other people here that have other theories of the atom, they're all at different stages of development. So we might be a step or two ahead in some areas than they are, and they might be a step or two ahead of us in another area. And so we learn from one another. Like it was through a meeting like this that we were told by people at Common Sense Science, by a fellow named Dennis Allen, that we weren't doing our science correctly. And we said, "What do you mean?" And he said, "Well, the rules for doing science were published by Isaac Newton in the book Mathematical Principles of Natural Philosophy." And he said, "You're not following those rules." And so we looked and we saw what the rules were, and we said, "Oh, we can change and do that." So we did. And then we found we had a better theory. And was that the most perfect theory? We don't know, but it was better than what we had before. And and what Newton said was how to combine the logical axiomatic scientific method with the empirical experimental scientific method so that the two work together. And what has happened in modern science is they don't work fully together. They're somewhat separated, and so that's not a good thing, but it satisfies the politics of the day. And who knows, 100 years from now, the politics may be different, and the things that they don't like that we're doing, they'll like in the scientific community, and they'll go from there. But we don't know.
Well, I wanted to get back to discussing, like Harry's point, which is why, even though a lot of work has been done on these toroidal ring structures, that basically mainstream really doesn't pay much attention. Now, so this toroidal ring structure, though, is central to, I mean, it's basically the foundation for the rest of the theory.
Yes.
But I would argue that is still a fundamental assumption
No,
as
it's not an assumption because we make these experimentally. Um, the first person who worked on this area was Arthur Compton, and he discovered the wavelength of the electron. Now, at the time he discovered that, people said, "What? How can a particle have a wavelength?" Well, in quantum theory, they made it so it could, but anyway, but his last graduate student, Winston Bostick, he was able, from just like I could take the plate and put it in the water, and make two toroidal rings, he put a disturbance in the electromagnetic field and made these toroidal rings out of the field. And he was really shocked when he did that because the wavelength of the electron, guess what? It was the circumference of the ring. Wow. Then he was also shocked because he found that he couldn't break the ring into pieces. It was so strong. He could make it go away by bringing an anti-electron positron together with an electron, and they would then the two rings would disappear. He didn't know where they went. All he knew is he couldn't find them anymore. And but he knew they were strong, and so he tried to make a bottle out of them to contain controlled thermonuclear fusion, because there was no known man-made material that could contain them without deteriorating and crumbling. And so he found that the toroidal ring was strong enough, but he wasn't able to build a bottle out of them to hold it, a container. And so you can build an atom out of it, but the atom is not a container in the sense that you can put something inside and take it out. And so anyway, that's what he found. But he found that the strength experimentally of the toroidal ring was the highest known strength of anything that had ever been observed in science. And it was the ancient Greeks and Indians and Moses claimed it was uncuttable. And that's what he was finding, although he
So
wasn't a religious
how did
person.
he exactly make this? I mean, was he making a ring in plasma? I mean, I'm familiar with like making smoke rings and stuff like that, but what was he doing?
He was disturbing the electromagnetic field, and just as if I have water and I have a smooth continuum of water on one level, you move a plate through it, you make a ring, and the ring is usually about 2 or 3 feet in diameter, and
Yeah,
it
that's
will
what I'm wondering about because the ring of an electron would be so incredibly small. How could he even observe that it was
the
a toroid?
toroidal ring can be made different sizes because you see the toroidal ring responds to its environment. If you put it in a certain environment, you can make it bigger. He made toroidal rings on the order of 1 to 2 inches, but the electron is much smaller. But you can make the toroidal ring smaller. In fact, if I bring the toroidal ring into certain fields or next to other toroidal rings, they shrink.
So that's
So
my question: is that if he created a toroidal ring of like 1 or 2 inches, how did he do that? Was that a toroidal ring of plasma, or what? It sounded like it was like some kind of plasma.
it's in the field. He was using plasmas to help generate the fields and the disturbances in the fields, but the actual particle is made of field. And when we have a toroidal ring, the field has certain properties. It's a standing soliton structure. It's like a standing wave with very long lifetime. I mean, thousands of years. And the what he observed was that if you were to measure the field around this soliton structure, it had a 1/r dependence, just like the electromagnetic field from a charge does. And what we're seeing is, and this is what a lot of people don't understand, is that when we were developing electrodynamics, and we were making the empirical laws, we had to put an equal sign in these laws. So we knew the electromagnetic Coulomb force was a 1 over r squared force. But we didn't know what the constant was, so we put a constant in there and we called it charge. And Newton did the same thing when he was working with force of gravity and the force of inertia. He had to put a constant in there to put an equal sign, and he called it mass. But neither Newton knew what mass was, nor did Coulomb know what charge was. They just
I'm
used.
still trying to understand what this experiment was. So you said that he was making these things out of fields, but
Yeah.
like if you have like a magnetic or electric field, those things are completely invisible. So
No. We have all kinds of instruments that we can observe the field, and that was how he was able to take a picture of it. He took a picture of these toroidal rings made just of fields, not of particles. But the fields had the properties that we have been associating in the electrostatic laws with charge. But charge was something we never knew what it was.
Bill,
Yeah,
can I interject for a second?
sure.
You were saying he took a picture of it, but what you were saying too is that he actually created these fields in plasma. So what he really took a picture of is the plasma writing the shape of the field within the toroidal ring was in the shape, or was writing the wave that was in the ring. So it was really, it made it visible because of the plasma being there, but the field was actually in the electromagnetic field with the plasma writing. Is that correct?
Well, he was able to stick a metal prong into this environment and capture the toroidal ring and pull it out of the plasma. And it would stay stably on the end of this toroidal ring. And I don't know if you know about it or not, but he worked with some people at MIT to make a new type of jet engine in which he took one of these toroidal rings out that was about an inch or two in size, and he put it on a prong, and he put it in where you would normally explode your gases in a jet engine, but he made the engine with no, so it was airtight vacuum, and he put this in there, and then he used something like a microwave oven, but it was that could pump energy, more energy into the toroidal ring, so he could bring the temperature of the toroidal ring up to millions of degrees. Then this engine was put in a jet plane, and they let air in the front side of the thing, and they would heat the air up and throw it out the back side because it was very hot, and give you your propulsion. And that jet plane was demonstrated for DOD, the Air Force, commercial airlines, and NASA. And they flew that plane around the Earth with no fuel, just from the energy stored in the toroidal ring. And the toroidal ring, you could see it had a lot of you could take a picture of it because of all the energy coming out of it. And so anyway, that
Right,
is
the
one of the.
propulsion still would have been standard propulsion where you were ejecting the hot gases. It would just have been a different methodology of generating that, accelerating those gases using the toroidal ring, the
Right,
vortex
right,
of the toroidal ring to do the acceleration. That's
right,
understandable.
right, right. And the jet plane could fly at Mach 17, which means it could go to any planet in our solar system. And so that
I
was
think,
quite a demonstration they did. And they had
yeah,
no fuel on the plane.
I think part of the confusion here might be that when we look at the toroidal rings that he was looking at and the toroidal rings that you're talking about, that's the structure of the basic electron. The toroidal rings of the basic electron are basically electromagnetic waves, period. There are no particles
That's
within
right.
this wave.
Right.
Within this wave structure generates the particle.
This toroidal ring has the properties that we
Of the particle.
associate with charge,
Exactly.
but it's not there is not a quantity called charge. It's just that when you have this soliton standing wave, the wave, if you look at the electromagnetic fields, the way
Correct.
they fall off, if we show a picture here, it looks like that's a finite size, tightly bound ring. But really, the electromagnetic fields are coming off in all directions from this ring, and they're producing effects in the electromagnetic field at a distance, and we associate those effects with what we call charge. And that's the way
Correct.
we've
100,
always looked
100%
at it.
agree.
And mathematically, it has worked for a long time because these toroidal rings are small, and we have never noticed the difference. But when you make a bigger
Correct.
one, you can notice the difference.
Right. Now, I've noticed on your toroidal ring, I've brought this up a time or two before, that you have the electron designated as a toroidal ring that has the major axis and minor axis, where the minor axis is quite small compared to the major axis. And I always see that as being an electron in linear motion, or in the presence of an unbalanced field that puts it into that condition. But I see an electron otherwise as a toroidal ring wave shape that is the major axis and minor axis are of equal magnitude, where you get electrical radiation that is symmetric in all directions.
You're breaking up there. But my question is, how do you get a wave out of a toroidal ring? I mean, if it's a ring like this, I would think it'd be more like a flow, like a smoke ring, and not have anything to do
Well,
with wave.
well, for instance, if you make these toroidal rings in a swimming pool, you can see the toroidal, vortex associated with the ring going out to all the edges of the swimming pool. But when you shine a light like the sun through the water and get an image on the bottom of the pool, you see what looks like a ring. And that's just due to the optical properties of the water with this type of wave. And so what you see is that the um, you
But
can
that is a circulation, not a wave. You know, a
it, it,
wave
it,
is,
it's kind of, yeah, it's kind of like a vortex circulation. That's right. And
yeah. But I think Cornelius was trying to say that it was kind of a standing wave, because I hear this, that, electron is like standing wave, but that seems to be in contradiction to this toroidal thing, which is more like a vortex flow.
Well, the problem that comparing the toroidal ring in a vortex flow of fluid and the toroidal ring in an electromagnetic field is that in a fluid you're working with Bernoulli's principle to keep the toroidal ring going, and that doesn't exist in an electromagnetic field. You're working in an electromagnetic field. You're working on the balance between the electrical and magnetic field, or properties of the field, working against each other to hold the wave form in the shape, but you don't have an actual particles moving around, and so you don't have mass moving around like you have in a fluid toroidal ring. There's no mass there. It's strictly electromagnetic charge. The mass is, again, a property of a particular wave pattern. It's not a property of the field material itself.
in this approach for the toroidal ring for the atom, and determine the mass of the atom and the mass of the electron and stuff like that, um, if you had only one toroidal ring that made up the electron, then you couldn't have the property of mass. But if you had three toroidal rings, then mass could be defined as the kinetic energy of vibration of the three toroidal rings. And that produces not only the mass of the electron, but it also lets you determine the temperature dependence of the mass. And so there's a lot of features that you can start to measure once you have a proper or this type of a model. And so the Russians, for instance, have measured the temperature dependence of mass. And according to most theories, that what they're measuring doesn't agree with any of the theories that are out there, any of the politically correct theories. It doesn't agree with E equal mc squared. And because you'd have to interpret that as E equals the vibrational kinetic energy of atoms and things of that sort. And then as you break the structure of the atom down, you can't have those vibrational modes, and so your mass will increase with temperature, and then it will drop, and then it will increase again with temperature, and then it'll drop as you break apart certain structures at certain temperatures. And so that data has been out and been reproduced in 20 or 30 laboratories around the world, and people are shocked because it doesn't agree with relativity theory. It doesn't agree with a lot of things. And
I don't see how you can emulate the spherical shape of mass or spherical characteristic of mass with only three. It seems like you would need at least four to emulate that. I mean, you and I, we differ a little bit on how we come up with mass generated as a waveform.
well,
But
why do you think the electron is spherical?
well, because electrical charge radiates in all directions equally from a electron that is not accelerating. You don't get any magnetic field from an electron that's not accelerating. They're not moving linearly.
Well, I was at the College of William and Mary, and we did the fundamental experiments at extremely low energy of electrons interacting with electrons. You know, we were working to like 1/100th of an electron volt, 1,000th of an electron volt, you know, those kind of energies. And
Right, but
we were able to determine the shape of the electron was not spherical.
well, but the thing is, you're using an electron to measure an electron, and automatically, as soon as you put an electron in the field in the range of field of another electron, you're going to distort the shape of that electron and automatically give it polarity.
Yeah, but by doing it at different energies, you can remove some of those effects. And you know,
But
when
you're
you
going
do scattering, of any particle off of a nucleus or another elementary particle, you're going to affect that particle before, you know, just because you're scattering on it. And then what happens to the scattering, you have to determine how much was due to different things. And so you try to eliminate as many of those effects as you can to get to the basic ideas. And
right,
So
but
what is the
an
experiment
electron
you
is
went
always
to?
going to be.
I mean, you made it. You did an experiment. You said it's not spherical. So, what shape is it?
toroidal.
Toroidal, yeah, of course. That's what it's going to be as long as it's in the influence of something else that's distorting its shape from being spherical. And you have to realize that since the electron has no real limit to its size, as Bill says, that we show it as a nice toroidal ring, but it really is wave shapes that continue out in the inverse square law. It's always going to be in the influence of anything you try to measure it with, because no matter how far away that measurement item is, it's influenced, and the closer it gets or the faster it moves, the more influence it will give you. So you're
Yeah.
not going to be able to measure it as being spherical, except for when you look at the like a static electrical field. You'll notice, the field is basically spherical in shape. Now you could also comment, well, that's because of the combination of all electrons mixing randomly together. They cancel each other out, and you overall get a static electrical field that is symmetrical, and that's a difficult thing to discern too when you try to
Well,
measure in a single electron.
when we accelerate electrons and do electron-electron scattering with higher energies, the
Right.
electron shrinks.
But as soon as you accelerate an electron, you turn it from that toroidal ring that has a major and minor axis of equal size to one that has a major axis of a larger size than the minor axis, and then you start getting the donut-shaped toroidal ring, which then gives you magnetic polarity of north and south based on the donut shape. If you're not accelerating it, then you get no magnetic field from the electron either.
Well, you see this Formula 8 on the screen there? We're able to derive.
It's kind of hard
We're
to
able
see
to
much.
derive the Planck's constant, and that shows that if the ratio of the R to the R naught is nearly comparable, you will not be able to claim Planck's constant.
Right, but then again, you're looking at the electron in motion when you're doing those measurements, or you're looking at the electron in the
Well,
field of the measurement.
this is a stationary electron we're looking at here.
Well, if it's stationary, you can't measure it. It's got to be interacting with something, or you can't measure its existence even.
Well, you can measure the fields of it, so you know. Well, let's go on to some other topics. So
Okay,
we've
that
spent enough
sounds good.
time on that one. So I guess the the problem that we have faced at Common Sense Science is we have got to, if we're going to change the structure of an electron to be made of toroidal rings, then we have our proton has to be made of toroidal rings, neutrons have to be made, pions, muons, uh, kaons, and all these different elementary particles. And we should be able to explain what their geometrical structure is and predict their mass at zero velocity. And we should be able to predict all of their decay modes. And that's what we've been able to do. And so, and the standard model has been able to do it with 19 to 29 adjustable parameters representing unknown physics, but we just use electrodynamics alone. So we think that the simplicity arguments in our favor, and the fact that we get it such high accuracy in terms of the measurements that we predict. But
Although,
we're not
as you
through.
pointed out, though,
Go
as
ahead.
you pointed out, Bill, is that even according to your philosophy, is that by logic, if your fundamental assumptions are not correct, and it really doesn't matter how much you can predict. And that would kind of be my main objection. I mean, you say that this thing has been shown to exist.
Yeah.
Although I
Well,
think
see,
probably mainstream would probably disagree with that, and it's probably the main reason why they wouldn't accept that, is they're not accepting the experiments that you are mentioning, or maybe they just don't know about them.
well,
But
they're published in like, see, this one here, this paper is International Journal of Fusion Energy, because they were going to try and make a bottle to hold all these controlled thermonuclear fusion products that were being made, and we were trying to generate energy and contain all the byproducts within a bottle. And so it got these been published in leading journals, but people just ignored them after a while when they realized the ramifications of the work. And so that is kind of bad. I met the author of this paper. He was working at New Jersey Institute of or Stevens Institute of Technology in Hoboken, New Jersey, and but people were just ignoring his work by that time. I met him
well,
in
I
the.
mean, I'm kind of sympathetic to that. I mean, for me, I find these. I mean, I know there's been a lot of work in these toroid rings, but I think there are a lot of hooey myself. I mean, there's
Based
things
on what?
I would base it on the things that, for example, they have the fractional charges. There's supposed to be a fiber wrapped around a 1/3 fractional charge. Now, there are a couple of problems with that. One is that if charge is made out of charge, then it would tend to explode itself. So that's a problem. Now, I know that they say that the magnetic field around it is supposed to be bottling that thing up. But I think you need to then have an explanation of how the magnetic field works and whether it's actually active at that level, because it might not be.
Okay,
And
I can answer some of those questions. The laws of electrodynamics say that if I have charge and it's got smaller pieces of charge, and I try to put them together, they're going to repel and come apart. But it also says if I have a continuous loop, not a particle going around in an orbit, a continuous loop of charge, that it can stay bound due to the electric and magnetic forces. So it doesn't violate any of the laws of electrodynamics.
I just
So
find it
that's a
hard to
problem
believe. I mean,
that,
it's nothing I can prove, but it just seems highly unlikely that that structure would hold itself together any more than, you can have like three magnets balancing each other. And, magnetic field and electric field are extremely slippery.
On what?
Anything you put together magnetically tend to just fall apart or they'll collapse or whatever. So,
So in other words, you don't really have a reason. You just have I don't like this theory, so I reject it.
well, I just don't see anything in the real world that would actually do that. I mean, all the toroidal rings I know about would immediately fall apart, and if two toroidal rings come in contact with each other, they'll rip each other apart. So
right.
all of my experiments,
Well, what are you going to say about Winston Bostic's experiments? He took these toroidal rings and put them in reactors, which would destroy any known material known to man, and they were not destroyed.
Well, I would say that's very interesting, but I really have to, my criticism with that be that may have actually had absolutely nothing to do with electrons. You may have created these toroidal rings, and they may have done that, but he wasn't actually studying electrons.
Why does he call it the morphology of the electron?
Because that's what he thinks it is. Honestly, I mean, that's what he thinks it is. But my
That's what
criticism would be,
all the people who worked for Arthur Compton thought for 50 years in all their experiments. Yes. And you haven't done any of those experiments, so you need to figure out, do I take their advice? Do I accept any of their experimental work? Other laboratories reproduced it. And so what you're saying is the interpretation is in the eye of the beholder.
well,
No, I think the problem that Franklin has is he's looking at mass. He's looking at fluid toroidal ring. Every example he's looking at is a gas or a water ring or something that has mass to it. It's a fluid ring. He's not looking at an electromagnetic because you can't look directly at an electromagnetic. You have to look at the effects of it. And so that's why there's an issue with trying to understand how toroidal rings hold themselves together, because it's looking at the wrong material for the ring to be in.
I mean, that's absolutely correct, Cornelius. I mean, that's my main objection. But you're saying that you have to be able to look at some other toroidal ring which isn't made out of mass, which isn't anything that we can actually study in real life.
But what Bostic did is he made a toroidal ring that was an electromagnetic toroidal ring, and he made it visible by having it within a plasma gas that you could see the reaction of the plasma gas to it. This is much like my theory or my view of the bubbles and the stress and strain on the surface of the water. It's not really the surface of the water, the particles of the water that you're looking at. It's the tension wave moving through the water that you're looking at that's doing the work. Here is the electromagnetic field that's doing the work, and you're seeing it visible through the injection of plasma that reacts to that wave, that makes it visible. So, and as opposed to just looking at water, where you have the mass and the Bernoulli's principle holding it together, it doesn't hold it together in the same way that the electromagnetic field would.
Yeah, but once again, I'm just kind of playing the devil's advocate here, saying why is it that mainstream doesn't accept this? So, and as you said, I think that is one of the main reasons that we have no real world analogs for these sorts of things.
But that's not true. I mean, it's just flat not true.
No, that is true. There's no.
We have all
I just put it. I mean, that's just not true. I mean, you're just making claims not backed up by any facts.
We have facts. I mean, we know what smoke rings do. We know what the rings in
I just posted Carton's Corner website link if you want to go to it and look at it. The guy shows pictures of toroidal rings.
Well, and I can show you pictures of toroidal rings too.
Go look at it.
But that doesn't prove that those are electrons. I mean, you can show me pictures of toroidal rings.
That's a non sequitur there, Franklin. Sorry, it's just a non sequitur.
No, I think it's quite relevant. I mean, I'm trying to tell you, why is it mainstream ignores this particular theory? So I'm giving you.
Well, I think Bill explained that. Earlier in that they use quantum mechanics. So what you have is you have quantum mechanics, and quantum mechanics is sort of fuzzy in that the way Bill explained it is it's all probability waves, and so therefore they just basically make the structure up out of probability waves.
Yeah, but this is another problem I think mainstream has with these kind of solutions, in that you're trying to make stuff up, but like, for example, Corey's, well, actually, everything's made out of waves is what you said. But I think mainstream has a very, very, very.
No, they use the concept of probability waves, or waves of probability, and quantum mechanics basically, it's sort of a vague, and so then they just kind of put in these, way they create a theory, okay, and the theory seems to work, or it works to their satisfaction. But what it is that's predicting is not predicting anything physical, it's just predicting a probability.
Yeah, so the things we're familiar with that are physical from classical physics, they are quite different from quantum theory.
Well, you have a different, to me, I mean, my feeling about this is that when the mainstream is talking about waves of probability, and so their whole theory is there's really not anything physical per se. It's just a phenomenological predictive um, um, mechanism. I'm trying to, in essence, basically, it's a computer method that predicts probability, and then they match those probability predictions against, experimental evidence. And so, okay, but is there anything physically there? On the other hand, what you're saying that there is a physical structure. They don't have a physical structure, and so what they have are point particles that move in accordance with waves of probability.
Yeah, now the ancient Greeks and the ancient Jains said that the monads had no physical properties that they would have recognized in that day. So if you wanted to have a property of charge, or you wanted to have a property of mass, you had to build a structure, and that structure had that feature, but not the basic monad or toroidal ring. And so that was how they described it in their day. And
I would say mainstream sort of doing the same thing.
I want to make a point about fluid dynamics. In fluid dynamics, you have to have a fluid which has some kind of tension in it, and all things that have tension in that manner are have fluid properties. So we have water, which is made of particles, but there's a tension between them, and that's what makes it a fluid. And
well, Bill, I have a question. I mean, this is my other serious objection against these toroidal ring structures, in that I don't see how their effects can possibly be long range if it has anything to do with fluid dynamics. Because I don't believe that, say, if the charge is due to some sort of rotation of that fluid, that, for example, if I set a vortex in a swimming pool, by spinning my finger, and I can create a very nice little vortex there. But at the other end of the swimming pool, there will be no way to detect that vortex is there, because it's just going to be completely swamped by everything else that's between that.
We don't find that experimentally. You should look at some of the things online. What you find is that if you have sunlight, the sunlight going through the water enables you to see the vortex.
Yeah, I know, but you can only see that within like inches or millimeters of the vortex. My objection to the toroidal ring is that there's no way it can have a 1 over r squared infinite distance influence.
Well, look at the
It has
picture at
anything to do with
Carton's
fluid
Corner
dynamics.
that who is it put that up there? Uh,
I
it
did.
shows, yeah, you if you look at those, I can see on the surface of the water, I can see the waves going away from the vortex ring with the 1 over r squared type uh, fall off. So
But
I
waves
can
can
actually
do
see that.
that.
Now, I think in the case of when uh, Bostic was making them in the laboratory, he found a way to see it too. And so, just as we could see it with sunlight here, I mean, you wouldn't have thought that the toroidal rings would show up so well after you made them in the swimming pool.
Well, not that they show up, but they're very localized phenomenon. Because this is
So
my objection that toroidal rings are very localized
have to
phenomenon.
be met for a plasma,
Uh,
and
yeah, I
just
have the
particles
same.
won't do it. Without you have to have a tension.
The only thing
There's a,
I can think that's long range would be like a wave. So if I put a speaker in a swimming pool and I, play music, I can hear that music all the way on the other side of the swimming pool. But if I just took that speaker and spun it in a circle, there would be no way for me to detect that there's a spinning speaker over there. Only
It
if
Right.
demonstrates exactly what, Franklin? I mean, that demonstrates your confused thinking.
no, that
That's
demonstrates
exactly.
that any spinning object cannot transmit its information over long distances,
But it's not an
which is
object; it's
what
a
a
wave.
charge would have to do.
That's the problem. You keep on going back to a fluid or a particle type motion. It's not. It's not. And the idea about keep on using a fluid in a swimming pool is not a good example. A fluid in a swimming pool is already particulate. It's not electromagnetic. It's not a field. This is why I can keep on going back to it's not a fluid type either. It's a solid continuous field that can only propagate, and the only thing can move through it is a wave.
Well, I could see that point, but then you would have to basically be making up a kind of scenario which can't be physically demonstrated.
Another unsupported assertion on your part.
That's
No,
why
that's
we have
perfectly
to have.
supported. I mean, Cornelius is saying that I can't.
Everything you say has no support or basis.
It is demonstrated. It is demonstrated even by the tension on the surface of water, because there's tension between those particles, and that tension between those particles is supported by the fact that they're continuously connected, because the particles themselves are not actually separate. The particles themselves are wave structures.
Well, also they have electromagnetic fields associated with each of those atoms and molecules in the water, and
Well,
that's where you get your tension.
electromagnetic fields don't even exist. Actually, the only thing that exists is a tension field, which can then take the shape of a transverse wave in that field. And a transverse wave is where you get your electromagnetic characteristic in your field charge. The longitudinal waves are actually responsible for the mass. But I'm not gonna, change subjects at this point. So
Well, I think the real issue here for me is why is mainstream refusing to even fund or I know that Robert Keene, who's he
Well, hey, I give
basically
you the
only started
objections
doing
that
this work after he had
those are
retired from the
objections what
university.
mainstream is
That's sort
saying.
of a problem.
I mean, I gave you the objections. I'm pretty sure mainstream would probably agree with those objections.
What objections were they?
The objections are that physically people don't see this as being possible.
Well, that's meaningless. That's not an objection. That's just an attitude.
Well, sure, but I'm telling you that's the attitude.
And it's unjustified by any basis in logic or any facts or experiments or any basis in scientific method.
It's just complete, as we discussed, it's completely validated by what we can observe physically with toroidal rings. There's no toroidal ring experimentally that will do what the Bergman model says it will do.
That's just your opinion, unsupported by any factual evidence.
That is fact. That is total fact.
You can never see
Unsupported
the
by any
electromagnetic.
evidence.
You can take a smoke ring, it will disappear. That is fact.
So what?
You can never see the electromagnetic field directly. The only thing you can see is its properties, its interaction with other distortions, other gradients in the electromagnetic field. And that's what particles are. You're hooked on the fact that if I can't see it, it doesn't exist. But you can't see it until the electromagnetic field forms it.
Gentlemen, I have something that looks like photographic film, and it takes pictures of electromagnetic fields.
Well, we have things like, we also have things that can detect magnetic fields. They have these thin things. You put a magnet on it, and you can see the magnetic structure. Now, basically, that doesn't really mean anything other than, we can see that. So that's great, but, how does that really answer anything?
Well, if we can see the fields, it should answer all the questions.
Bill, your film can't take a picture of the electromagnetic field unless it has a gradient in it. Because if it didn't have a gradient in it, you would have a pure white picture or a pure black picture. It has to have a structure.
If there's no structure in the field, you're right. But if there's any structure, it shows it. So if I have a soliton in the field, I can see it.
That's what I'm saying. You can't take a picture of it until you get distortion. So you can't really see it until a particle is formed.
Well, I can just put a charge there that's at rest, or I can put a magnet there, and I can see the fields.
Well, that charge or magnet is an extension of a particle.
That's what the field is.
That's what I'm saying. So you still have a particle in order for you to take a picture of it. It's just that you're taking a picture of a portion of that field instead of the central point, which is the particle.
Well, if I have a strong magnet and I'm a foot away, I can see the field from that magnet a foot away.
That's right, but that magnet field originates or focuses from the particle. So just move your camera towards that, and there it is. See,
but I don't need to have a particle. All I need is a field. I can take the
field. No. Without the particle, you can't see the field. You can't. There is no field without a particle.
Well, if you mean toroidal ring, that might be something valid there. But anyway, that's fine. To go ahead and give your opinion there.
Well, it seems we didn't get very far into explaining, how these toroidal rings actually form into atoms.
They form by geometrical structures that balance the electric and magnetic forces. They were documented in experiments with magnets, and there is no such evidence for any other model of the atom that the politically correct scientists use.
So, like, I brought back up the pictures here. So we only have a few minutes here, but I did want to let people have some idea of what the atoms look like. So, like, you have your figure 5 here, and
mainstream uses the Helmholtz equation, and I haven't heard this name mentioning for the atomic model. It gives a perfect explanation for all these atomic spectra.
No, it doesn't. It doesn't do a single spectral line of any element in the extreme ultraviolet. Not one.
It does. It does. No, it uses the harmonic spherical harmonics, and it uses the spherical Bessel functions as solutions, and these give these spectra. It's you can prove it immediately mathematically.
Listen, I am the world's expert on pionic, muonic, kaonic atoms, and yes. I can tell you that's not true.
You say that it's not true, then prove that it's not true mathematically, because these are mathematical functions.
Yes, I know how to solve the equations, and I
So
do them,
if you don't,
and I
why
publish
do,
papers on them, and I can tell you there's not one of them that can do any of the experimentally observed lines in extreme ultraviolet. Not one.
they have modes, and these modes are exactly similar to the spectral lines.
For the outside of the extreme ultraviolet, in half of the lines they can predict it, but the other half they cannot.
What equation is this that you're talking about?
It's the Helmholtz equation. I have
What
pointers
equation
to
is that?
Helmholtz. Um,
I'm not
I
familiar
I
with the
gave
Helmholtz
I
equation.
gave the pointer to it at the chat box. Uh, I I it's somewhere.
Well, in any case, we're getting toward the top of the hour here, so I'm going to try and summarize. So today we had a talk from Bill Lucas, and we had like a kind of like a history lesson of atomic theories. And Bill was pointing out some of the information that would data that would support, say, his atomic model. So I know the last slide I have here is of just a second. We got a lot of noise coming in here. See if I can find out who that is. Okay. Okay, going back to this, our summaries. And but then we started getting into the basics of Bill's theory, which was the Bergman toroidal ring loop of the electron. So we did spend quite a bit of time discussing, how does that work? And we didn't get too much into the particulars of the atomic model, although that paper is available on the internet where you can purchase a donation on the Common Sense site. And that appeared to be based on basically using ring magnets to justify what we observe as the shell structure in atoms. So maybe we'll have to get into that more a little bit later, but we're out of time for this week. So thanks for coming, and please come again. We will continue discussing these topics next week. Actually, let's see, the CNPS conference is actually next week. So perhaps on the 22nd next week, I'll be reporting on what has been talked about during the conference, which will be happening this next week. So we can look forward to that. All right, but until then, that does it for this week's Morning Science Chat.